These are the notes for 6.1c, continuous random variables. With a continuous random variable, it is different from a discrete random variable that we've been talking about in the previous notes. A continuous random variable has an infinite number of outcomes with no gaps in between the outcomes. The probability distribution of x is described by a density curve, and the probability of any event is the area under the density curve corresponding to the event. Here are a couple of situations to think about. You'll determine right now if these are discrete or continuous. You may press pause now. When you think about whether these are discrete or continuous, you want to imagine if there is a gap in between the outcomes, or if in between outcomes there's an infinite number of possible outcomes or events. So the following on the left are discrete because there are no possibilities for outcomes in between their outcomes. So for example, a dice roll can have values of 1, 2, 3, etc., but you can't have a value of a dice roll of 1.5. Same thing with the number of correct answers on a multiple choice test. You can't have 2.5 correct answers. You're either going to have 1, 2, 3, 4, etc., as well as physical flights out of an airport. You'd either have 1 flight, 2 flight, 3 flights. You could say a flight is half full, but that doesn't necessarily mean it is not a flight. A flight is still defined as a flight. The fullness of a flight doesn't matter in terms of a flight out of an airport. The following on the right are continuous because there's an infinite number of possibilities. A person's height, someone could be 5'9" or 5'10", or 5'9 and a half inch, or 5'9 and 3/4 inch. Similar to time in a race. You could finish a race in 10 seconds, 11 seconds, 10.5, 10.2 seconds. Similar with weights and lengths. So here's an example of a continuous random variable. In often cases, we may look at these as normal distributions. But in this problem, the weight of 3-year-old girls follow a normal distribution pattern with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. So what's the probability of randomly selecting a 3-year-old girl that is 28 pounds or lower? We would treat this like any other normal distribution problem that we have done in the previous chapter. One way to do it, we would need to calculate the z-score. So using the z-score formula, we'd get 28 minus 30.7 divided by the standard deviation of 3.6, and we would get negative 0.75 as our z-score. We would then need to go to our z-score table and find the probability associated. And we would find that the probability of randomly selecting a 3-year-old girl that is 28 pounds or lower is 0.2266. Here is the graph of that normal distribution with the area shaded that represents a z-score of less than negative 0.75. And this would be the calculator way of how to determine that. Start with calculate, menu, probability, distribution, normal CDF. Keep your lower bound at negative 9s, as I like to call it. Upper bound negative 0.75. Mean of 1, or mean of 0, standard deviation of 1. This gives us the same probability value that we had from the table. Now, we could also graph that distribution here. We would just have to do it within the list and spreadsheets. So once I'm in here, I could do menu, statistics, distributions, normal CDF, same things as we've done before, and this time I'll include a draw, shade the area. So now I have the probability, which we found earlier, as well as now a shaded graph that shows us exactly what we saw earlier from Desmos. So you are able to get your graph shaded and the probability in the list and spreadsheets. There is another way to calculate these problems without using z-scores, and we'll go over that right now. You will need the key numbers of 30.7 as your mean, 3.6 as your standard deviation, and 28 as your value that you are in question of. To do that, we would need to set up similarly. Keep the negative lower bound the same. The upper bound, will actually make the upper bound the x value in question. Change the mean and change the standard deviation to the problem standard deviation. So this was the x value in question. This was the mean of the problem and the standard deviation of the problem. And you see that we get the exact same thing that we got previously. This is kind of cutting out the step of having to z-score everything. And again, if you use your calculator in free response, you need to write out this portion with the labels of lower bound, upper bound, mean, standard deviation, or else it won't count. Okay. Similarly, we can show the graph that goes along with this in a similar fashion. Again, this time I'm going to change it to the numbers in question without using a z-score. 30.8, no, it was 30.7 and 3.6. Also shading the area. And once again, we see the exact same area. Oops, sorry. We see the exact same area that we calculated, but this time factoring in that the mean is 30.7 and then with 3.6 as the standard deviation and all the values associated with it.